let's go ahead and get started. So the first question we need to ask is, what is momentum? So momentum is the product of an object's mass and its velocity. So those two things multiplied together will give you momentum. It goes kind of without saying that in order for something to have momentum, it needs to be in motion. It needs to have a velocity. I like to think of momentum as a quantity that kind of reflects how hard it is to make something stop. So if you have a lot of momentum, it's going to be very difficult to bring you to a complete stop, opposed to something that maybe doesn't have very much momentum. In physics, we use a lowercase p to stand for momentum. I don't really know why. I guess everything else was taken. But the units for momentum are kilograms times meters per second, because the formula is mass times velocity. So kilograms is our mass and meters per second is our velocity. So here is our formula to calculate momentum. Pretty straightforward stuff. So mass can never be a negative number because it is a scalar quantity, right? So because of that, momentum does have a direction, and that direction comes from the direction of the velocity. Remember that at the beginning of the year we set this convention that positive is forward, right, or up, and negative is down, left, or backward. It just means negative really just means you're going in the opposite direction than you were initially. So that means that because momentum can be a negative value, that momentum is a vector. Momentum is directly proportional to both mass and velocity, right? When we look at this formula, this is not division, this is straight up multiplication, and there's no squareds or square roots or anything weird like that, so it's just a direct proportion between these two variables. So that means that if you have two objects and they are traveling at the same speed, the heavier object will have much more momentum than the lighter one. And here's my heavy object, and here's my light object. So in this case, if these guys were both going the same velocity, of course, Java would have much more momentum. So now let's talk about what happens when an object changes its momentum. So in order to change an object's momentum, you can do one of two things. You can change its mass, which isn't very common in our problem sets, but sometimes it does show up. Or you can change the object's velocity. You can either make it slow down or you can make it speed up. And when we change an object's velocity, remember that means that the object is accelerating. And if something is accelerating, that must mean that we are applying a force to it. So if we want to change an object's momentum, we must apply a force. Whenever we apply a force to that object over a particular time period, we are not there yet. Let me go back. It causes an object to change its velocity, which in turn changes its momentum, which is just what we reviewed on the previous slide. This force that we apply is called an impulse. And we denote impulse with the letter J, as you can see right here. So, go back. Impulse is equal to a force applied, a time interval, right? So if I apply a force to something over a certain amount of time, I will change that object's momentum. And it's really super important to understand. This is kind of tricky for some students, I think, at the beginning of this unit. But these three terms, they all mean the same thing. I can say impulse, or I can say change in momentum, or I can say force times time, right? That's what this equal sign means, is that each one of these things can mean the same value. And that's kind of confusing for some students at first, but we're going to do an example problem or two, and you guys will hopefully kind of see what I mean. So let's go ahead and take a look at the first example. So in this one, we have a ball of mass 0.25 rolling to the right at 1.3 meters per second. It strikes a wall, and it rebounds to the left at 1.1. So what is the change in the ball's momentum, and then what is the impulse delivered to it by the wall? So we want to know change in momentum. So let's take a look and see what's happening in this example. So I'm going to exit out of this real quick and go to my have a wall, the ball is traveling here at 1.3 meters per second. It's going to hit the wall and then rebound back in the opposite direction, and it's going to go at 1.1 meters per second. So the first question is asking about the ball's change in momentum. So first of all, I would need to find its initial momentum, figure out its final momentum, and then subtract the two, right? That's what change means. So we're going to do this just like we always do it. The final momentum, let me go through this real quick, a little slower. So we have final momentum minus initial, and that will give us our change or our difference. So in this case, we have not only a velocity change, but we have a directional change, right? We have the ball traveling towards the wall, and then the ball is traveling away from the wall. So let's figure out our initial momentum. Initial momentum in this case is going to be the mass of the ball times its initial velocity. And the initial, I'm sorry, I forgot what the mass was. 0.25. Yes, 0.25. Okay. 0.25 times its initial velocity, which is 1.3. That gives us an initial momentum of 0.3. 0.325 kilograms times meters per second. Okay, so let's figure out our final momentum now. Now our final momentum, like I said, involves this directional change. So our mass is still the same, and now our velocity is 1.1, but it's going in the opposite direction, so that negative sign is going to become super important. 0.25 times 1.1, that gives us a momentum of negative 0.275. I know there are times when I'm like, the negative doesn't really matter, but in this case, when you're trying to find the change in momentum, it's kind of important because that directional change does play a part. So this is our final, and then this is our initial, so all we have to do is subtract them. To find our change. So negative 0.275 minus 0.325. So that is negative 0.6 kilograms times meters per second. This is our change in momentum, right? Or our difference in momentum is this value. So let's go back to our PowerPoint. Okay, change in momentum, negative 0.6 kilograms times meters per second. And then the second question is, what is the impulse delivered to it by the wall? Well, remember what I said on the previous slide, that impulse and momentum are impulse and change in momentum are the same. So if the change in momentum is negative 0.6, then the impulse is also negative 0.6. Now, for impulse, we have two different units depending on what we're talking about. In this case, we found the change in momentum, so it's kilograms times meters per second. But another unit for another unit for impulse might be newtons times seconds if we're looking at the force and the time. Okay, so in order to experience an impulse, right, in order to experience this change in momentum, you have to apply a force, which means that there has to be a collision or a short interaction between two different objects. In the previous example, it was the ball and the wall collided with one another. But it may be like a soccer ball in your foot, or you could get in collisions with cars, right? Your car and another car, you're going to change each other's momentum. So you'll be experiencing an impulse. So if you want to increase your impulse and therefore, increase your impulse and increase your change in momentum, you can do one of two things. You can increase the force you apply to the object, right? You can hit it harder. Or you can increase the time that the force is in contact, right? So you can hit the object harder faster. And this concept is really common in sports. If you play any sport that is like a contact sport like this, like golf or tennis or baseball or whatever, your coach probably has talked about the idea of following through. Follow through with your swing, follow through with your kick. Make sure that your foot is in contact with that ball as long as possible. Because if you increase that time, you will increase the ball's change in momentum, which means that you will make it go faster and farther. All right, so impulse can be graphed if we look at a force versus time graph. If we look at a graph like that, so that means your force is on your y and your time is on your x, then the area that's underneath this curve would be the impulse on the object, because force times time equals impulse. Impulse graphs can be pretty complex. I'm going to try my best not to give you guys any ones that are going to make your brains explode. But sometimes it's helpful to think about what the average force on the object is instead of the max. But we're going to do a couple of examples where you find both. Okay, so here's just a quick conceptual idea. We have two force versus time graphs. This one here, 300 for 5 milliseconds. And this one is 150 newtons for 10 milliseconds. So graph A, this one, is the force versus time graph for a hockey stick hitting a 160-gram puck. Graph B is the force versus time graph for a golf club hitting a 46-gram golf ball. Which force delivers the greater impulse? So remember that impulse is force times time. So we really just need to find the area under the curve for both of these. So this one would be 300 times 5, and this one would be 150 times 10, which in this case is exactly the same, right? 1,500 and 1,500. So both of these objects are going to experience the same impulse. The follow-up question to this would be to ask which object will be going faster. Well, now that we know the impulse, we would need to take into account the mass of the object, right? Because the smaller object will end up going faster if it receives the same impulse as the larger object, right? Same amount of force essentially to both of these, or force times time to both of these, but this one is much smaller, so it will end up going much faster. Okay, here's another example. It makes us actually calculate it instead of looking through just a conceptual like little check thing. So a rubber ball experiences the force shown in the graph as it bounces off the floor. So most of the time, force times time or impulse graphs look like this, where it's like a really sharp spike, because they're showing the collision between two objects, in this case the ball and the floor. So you'll see a really sharp spike in a lot of these, which represents the collision. What is the impulse on the ball, and then what is the average force on the ball? So let's answer the first question. What is the impulse? So part A, impulse is force times time. In this case, it will be the area under our curve, right? And in this case, our area is this triangle. So we have to do impulse is equal to the area of that triangle, which is 1/2 base times height, or 1/2. Our base is 8 milliseconds, and I'm going to be really picky with the units right now. So 8 milliseconds, if you converted that into normal time, it would be 0.008 seconds times the height, which is 300. And that gives us an impulse of 1.2. And we can say newtons per second in this case. Okay, the next question is asking for the average force on the ball. So, average force, if we have this graph, this is not your average force. This 300 represents your maximum force that is applied to this object. It doesn't represent your average. To get your average, you would need to take your impulse and divide it by the time. Why? Well, this is going to tell us if impulse is force times time. If we take the total impulse and we take the total time, we'll get the average force applied to it over this time period. So 1.2 divided by 0.008 is 150 newtons. And in this case, I know it's really tempting to just say, oh, well, that's just half of the max. It'll always be half of the max, but it won't be. It depends on the shape of your graph. So just be really careful with that whenever you calculate average force. Okay, this is the last example. On this one, we have a baseball thrown with a speed of 20. It's hit straight back to the pitcher at a speed of 40. The impulsive force of the bat on the ball has the shape shown in the graph. What is the maximum force that the bat exerts on the ball? And then what is the average force that the bat exerts on the ball? All right, so we have a mass of 150. We have two different velocities, right? We have an initial and we have a final. So let's look and see what's happening in our problem. It's being thrown with a speed of 20. So that is our initial velocity is 20. And then it's going to be hit straight back towards the pitcher at a speed of 40. So these are going in two different directions. And it doesn't really matter, I don't think too terribly much, which way you picture it, as long as you make one direction negative. So I'm going to make the initial velocity be 20, because in my brain, the initial velocity be negative 20, because in my head I'm imagining thrown towards I'm imagining that the batter is our reference point, right? So you're going towards the batter, and then the batter will hit it away from him, so that will be in the positive direction. But you can do it either way. All right. And then we've got this nice little curve, or this nice little graph, but we don't have a maximum force, so that's what they're asking us to find. So I know that the area under this curve, or the area in this triangle, will be my impulse. But I also know that my impulse equals change in my momentum. So I have enough information here to calculate what my change in momentum is. So let's go ahead and do that. Final momentum minus initial. So my final momentum, I'm going to go ahead and convert this to kilograms. 0.15 times, I don't think I'm going to go to my whiteboard here for this. All right. So PF minus PI, 0.15 times our final momentum, or our final velocity, which we said was 40. And then our initial momentum is 0.15. And then I decided, or I chose to make that initial velocity be our negative number. So when we do that, we get 9, positive 9. So I know that my change in momentum is 9 kilograms times meters per second. But I also know that this is the same thing as my impulse, which I know to be force times time. So essentially what I've done is I have calculated my change in momentum, which is the area under my curve. So do you see how all of those kind of mean the same thing? They're just different ways to calculate the same number. So this area is 9. And I know my base. I just need to find my height. So it'll be the impulse is 1/2. 0.6 milliseconds is 0.00006. 1, 2, 3. Oh, whoops. 120. Okay. Times height, and that equals 9. So now I just have to calculate whatever my maximum force is once the impulse is 9, we said. So when I do that, I calculate that my maximum force is 30,000 newtons. And then the average force that the bat exerts on the ball is going to be So the maximum force was 30,000. And then the average is just taking that momentum, right, or the change in momentum that we found before to be 9, the impulse is 9, and dividing that by the total time. So your maximum force was 30,000, and then your average force is 15,000. And again, this was another scenario where it was exactly half of the maximum, but that's always going to, I think that's always going to be the case if you have a nice little triangle like this, but if your shape is not a perfect triangle, that might not be the situation. All right, and that is it, guys. I will see you all tomorrow.